Hey everybody, Dr. A here, and in this video we're going to be providing some background information on what's known as combined loading. So let's go ahead and get started. Often applied loads cause multiple stress types to develop in members. So what we mean by multiple stress types is that you can have stresses acting in different directions or in different planes due to the nature of the applied loads on your entire system. So for different types of these stresses at a particular section, we must use the principle of superposition, or we can say we must superimpose the stresses that are acting in common planes and directions. So here I've already sketched out a table for us, and it's not that long of a table, but you might want to pause the video and start sketching this down, or rewind and sketch it down with me. But here we have 4 columns, okay? We have a stress type column, an action type column, the basic stress equation column, and the basic deformation equation column. Now, even though I've only listed 4 stress types, there are more than 4 stresses that you can encounter in mechanical and civil engineering applications. These are just the 4 most common stress types that we see over and over again. So this table could definitely be expanded and we could add to it if we wanted to. This is just meant to be a basic introduction to the idea of combined loading. So let's go through each one of these items real quickly together. The first stress type is called average normal stress, that we designate by the Greek letter sigma. And this is going to be perpendicular to your member's cross section, or normal to the cross section. This type of stress is also called axial stress, or axial normal stress, okay? The basic stress equation is force divided by area, and the basic deformation equation is FL over AE. Next is torsional shear stress. So we typically designate that with the Greek letter tau, and this action type is going to be parallel to your cross section. So it's a shear stress caused by twisting, and that shear stress distribution is parallel to the cross section. If you remember from your prerequisite knowledge, it typically varies from 0 at the center of a cross section to a maximum value at the edge of the cross section. Now, the basic stress equation for torsional shear stress is TR over J for circular sections. So if you have a solid circle or a hollow circle, that's going to be the governing stress equation for torsional shear stress. The basic deformation equation is the angle of twist, and that equals TL over JG. Again, this formula is valid for circular sections, so either solid circles or hollow circles. If you don't have a circular cross section, if you have some other shape, you're going to have different governing stress and deformation equations for non-circular sections. So I'm just including the circular sections here because these are the most common that we see in undergraduate mechanics of materials and structural engineering. For flexural normal stress, that's our third type of stress, we designate that with the Greek letter sigma, and that's also perpendicular to the cross section, a lot like average normal stress, except it's not uniform. This is a non-uniform stress distribution for flexural normal stress. Specifically, it's a linear stress distribution, okay? Now, we typically have a plus and minus associated with that, and that's going to be equal to my over I. And I'm going to put another note here. I'm going to say or mx over I. Now, the my over I or the mx over I will depend on what primary axis of the cross section your bending is about. Let's put a plus and minus there too. So if you have bending about the centroidal x-axis or centroidal y-axis, that's going to affect, are you looking at a centroidal distance in the y direction or the x direction? That'll also affect, are you looking at a moment of inertia about an x-axis or a moment of inertia about a centroidal y-axis? So this is just meant to be the basic basic stress equation. Depending on your specific problem, it could manifest itself in a different way. I'm going to skip the deformation associated with flexure for now. I'm going to come back to that in a minute. The fourth stress type is beam shear. We call that tau. That's going to be parallel to your cross section, and that's going to be equal to VQ over IT. Again, that's the basic stress equation. Now, notice that for the basic deformation equation, for flexural normal stress and beam shear, I don't have one equation. I have processes. So I'm gonna make a note of this. I'm gonna say these are processes. For example, deflection processes, that's the DEF, deflection processes such as the double integration method, energy methods, maybe that's Castigliano's method or virtual work. You typically learn about those methods in a structural analysis course or a machine design course. And I put etc. here. Etc. could also mean pre-derived formulas. So there's not just one formula for calculating deformations due to flexing or beam shear. There's typically a set of equations or processes. So that's why there's no defined equation there. Again, this is just meant to be a basic listing of these different common stress types to help us not only refresh ourselves of this knowledge, but also to figure out what should we add together if we have multiple of these acting at a section. So for average normal stress and flexural normal stress, both of these are normal or perpendicular to the cross section, which means that if you have both of these stress types acting at a particular section, you use the principle of superposition and you add their magnitudes together. Same thing goes for torsional shear and beam shear. Both of these are parallel to the cross section. So if you have both of these types of shear stresses acting at a particular section, you can use the superposition principle and add them together. You cannot directly add together normal and shear stresses though, because these are in two different directions. Okay, they're not acting in the same direction nor in the same plane, so you can't just simply superimpose them together. So you have to be very careful and you have to be able to visualize what direction and in what planes your stresses are acting. So hopefully you found this video helpful. If you did, please hit like and subscribe and look out for the next couple of videos where we have some numerical examples of this topic. Thanks for watching.